as is tradition, I guess I need to open this with a joke. And actually, I'm getting better at coming up with jokes like while I'm on the tram over here. So I think I've got two really good ones. Here we go. Well, terrible. By good, I mean terrible. So how many machine learning researchers does it take to change a light bulb? Answer, I don't know, but a Silicon Valley startup just raised $20 million to find out. So how hard could it be? And I got another more racy one, which I think is, I've always wanted to be good at one-liners. So here's sort of a one-liner. Did you hear about the machine learning researcher? She's in trouble with her uni boyfriend because he called it cheating, she called it cross-validation. That's one for the ML nerds out there. Yeah, so we have a huge show for you tonight, and we've got a big announcement as well. So, well, let's get right into it. So, okay, AI grant, this thing just happened, but you should definitely get into the next round. There's a lot of like free money out on the internet for people with ML ideas. So, aigrant.org. I applied with someone in the audience, Jarrell. So, I might put up the video. Is it okay if I play the video later? Yeah, okay, it's not too embarrassing? All right. Otherwise, we can just talk about it in the news. Secondly, we are going to apply again to create an AI accelerator, and this is part of the LaunchVic Round 4 funding. So basically, we're trying to get free money from the government, which is always good. It's matched, so the government gives you $500,000, and then you find investors to try and give you the rest. So for those of you who don't know, the concept of an accelerator is like basically what you need to make AI ideas happen. So we take teams, they say, hey, we want to be a part of it, we have an idea, and then you get mentorship and you get money to develop your idea, and finally, about after, depending on how long the program is, probably about a year, then you can look for someone to try and invest in your company. So if you're into that sort of thing, then this is happening. And importantly, I just sent out an email with a Google form. So when we apply for these sorts of things, clearly we want to say like, hey, we're legit, and there's lots of people waiting in the wings, like lots of Melburnians and Victorians who would want to be part of this thing. So if like you have an AI ML idea, and you want to like make it a thing, then this is like, we've literally been rejected for this before, so we're going again. Second time lucky, as they say, very, very commonly. But you should definitely, if you have an idea, say, like, do the form, like, it'll take like 2 minutes, and we'll put you in the application and say, look, here's all the people waiting in the wings who would want to do something like this if it existed. So hopefully it'll make our case stronger. So you can really help with that. And also, if something like this existed in Melbourne, that would be awesome, because it means that if you just have an idea, you can literally get paid to work on it, which is important because a lot of us so far have been working on things in our spare time. So this is kind of like, as the meetup has grown, it's kind of, I guess, growing the ecosystem here, and that's what we've sort of always wanted to do. So yeah, I remember the speaker we have actually has talked once before at this meetup, and he, we used to have it in a bar, and it fit about 60 people. So yeah, this thing's really grown, and we have recording now, so it feels, it's weirdly legit. I'm still drinking though. Oh yeah, we have a videographer, that's Takeshi, he's awesome. If you ever need any services, he's the guy I recommend. Okay, so this is the segment. Oh, actually, before, I have got a special guest, Alexar, who's going to do a little 30-second about him to get your juices flowing. So you want to come up here, Alexar? Yeah, now. I thought you wanted me to do this before. Yeah, surprise. Okay,
it's
so
just an introduction.
Yeah.
Basically, I want to share my problem. So if anyone knows anything about it, please come and share it. Talk to me. So we are working on a project, open source project for public sector. That's a content management system, but we want to provide the recommendation functionality. But we don't want to implement it ourselves. We want to use another service, whether it's a third party, whatever it is. But we want to integrate with a recommendation engine. But we don't want to use APIs to feed our content to that system. We want to use a third-party engine that doesn't require our content to provide us with recommendation for every piece of content that we request. I have been in talks where I know that there are systems like that, but I'm not aware of any open source solution on any good third-party service or application. So if you know of any, please come talk to me. Thank you.
Thanks, Alexar. Yeah, so if you can help Alexar out, definitely go chat to him afterwards. All right, let's do the news.
Andy,
Yes.
could you also say that we're live streaming and this feed is...
Oh, yeah, sorry. We are live streaming. If you're sitting kind of there, the back of your head will be in the live stream. So if you're shy about the back of your head, then move now, I guess. All right, cool, good. Sorry, I should have done that earlier. My apologies. All right, so here we go. Where's the news? Can I go to news? Hey, all right, so also, if there's a thing you want to stand up and talk about, like a problem you're working on or a problem you want to know how to solve, definitely this is the time to do it. So this is open to everyone, so what's happening? Andy G.
Self-driving cars.
Absolutely. So we've got self-driving cars.
Sail model.
And that's with Andy G.
And Cameron Leeson is here as well. Make create. Cameron's here.
What's your second name, Cameron?
Leeson, L-E-E-S-O-N.
Awesome.
Make create in front of me.
So yeah, Cameron's there and Andy G's there. So if you're interested in building a scale self-driving car, eventually to obviously scale up to a full self-driving car, then and I think you're racing them as well.
Yeah.
Yeah. Okay.
Yep. Building and racing.
So workshops underway now.
Oh, awesome. Excellent. Other news that's going on? Yeah, we got one there.
CNTK, which is Microsoft's machine learning toolkit, 3.2 was released just during the week with C# bindings, because prior to that he was on the platform with F#. So it's a really good tool.
Awesome. Yeah, I've been meaning to look at CNTK because I hear that it's really good for sort of recurrent nets and language modeling. So yeah, there we go. So yeah, news, obviously, that thing that I just said, which is the AI accelerator.
Smile.
Thank you. Sorry, I can't spell. It's a problem. Cool, so that's happening, and there is, we have a Google form thing. Fill out, we need mentors, so people who can, who want to be part of the program, and also people who want to enter the program, so founders. So seriously, if you want to follow your dreams, you should help us convince the government to give us money so that we can give it to you to follow your dreams. Alexa, you got one.
Anti-AI. It's I just saw them on a video today. I haven't had a chance to look them up, but they're Australian. Apparently, it's a wearable that detects AI voice and tells you it's AI. It's not. So that's what I
Cool. Oh man, hey, actually, topical, vote yes. If you have not got your thing before September 25th, you can go to the ABS and get them to send it to you again. So I think there's a vote yes thing here too. So there you go. We're doing our bit. Finally, there was that awful thing. It was that gaydar thing, that deep learning gaydar. Stanford. I don't even want to put it on the news. I just want to call them out and say, I can imagine the dorm room conversation they had when they came up with that idea, and it was really stupid. They need to get out of their dorm every so often. Damn Stanford grads. Going to be a butterball joke soon. Anyway, and yeah, so does anyone have like an idea they're working on they want to come up and talk about, or a question they have which they'd like to pose to the group? Okay, if you don't have one, but you should have one next time. You'll be tested. All right. Any other news? Otherwise, we'll finish it up. Awesome. All right. So here we go. Oh, should we play this? Should we play our video, Jarrell? We'll play it. No, there won't be time to play it after. Okay. Well, I'm just going to do this to embarrass Jarrell. It's only 2 minutes long, and I want to thank Laura for putting this together. This is. Oh.
Yeah.
billions of people in the world today don't have adequate access to medical care. A big part of solving this problem is automating medical diagnosis.
However, there are many challenges in applying machine learning to medicine, particularly in X-ray images. Firstly, medical data is usually unlabeled. And secondly, many machine learning algorithms do not give an explanation for their outputs. And without explanations, it's difficult to trust their outputs and potentially dangerous to act upon them.
Our solution has two parts. One, learn high-quality representations by pre-training unsupervised on hundreds of thousands of scans, which we now have access to. Part two, build in interpretability from the ground up. Our model architectures are fundamentally designed to allow interpretability.
We believe that this will be the first pre-trained, unsupervised, large-scale CNN model. And once trained, we intend to release this model publicly. And this is how our model works. In our preliminary work done after our initial submission for the AI grant, we've trained a classifier on top of our model. An example here learns the difference between chest X-rays with and without heart failure. Using normal techniques we've invented, you can see how our network interprets these images. From the top left to the bottom right, you can see the initial X-ray image, the network's conception of that image, and what that X-ray will look like if the patient did have heart failure. The heat map indicates the difference between the two and corresponds with our medical intuition that enlarged hearts are indicative of heart failure.
We've worked together for a number of years and have published multiple papers in this area, recently placing highly in the Prostate X competition.
We believe that receiving this grant will allow us to continue our work, and we're excited to see what other people can do with our models.
Why am I doing this?
Trust me, I'm a doctor with a big GPU.
Guess me every time. Guess me every time. Oh, I get clapped. Wow. Okay, you're too nice. So yeah, there's a lot of, seriously, check it out. There's a lot of free money going around on the internet. So get on that. The person that, oh, hang on a minute. Haha, yes, one T. That was magic. I have the implant. So Mat Kelcey is an incredible researcher, an awesome, friendly human being, and he's spoken once before at the meetup, and it was awesome. And that's when it was in a bar, and it was dark, and it was a great feeling. It did feel like we were sort of, getting into something that was just starting out, especially in Melbourne. So I am super, super excited and honored to have Mat Kelcey back. Yeah! And now we do the awkward laptop change.
Yeah.
Oh.
Can people hear me if I talk? Not really? I hate being mic'd up and stuff because I like to jump around. So.
There we go. Well, you can just, yeah.
Okay. So hello everyone, my name's Matt. It's really exciting to be here. Thank you so much for hosting me. Thank you, Amy, for your kind words. I don't think I'm incredible. I think I've just done some fun things, in the last year, and I'd love to share them with you. This is going to be a bit of a, I don't really think too much about my talks. I just like to sequentially think about what's happened and brain dump. So this is a bit of a stream of consciousness for some stuff I've done recently. And so it's deep learning for robotics. There's sort of three things, I guess, in this talk. There's robotics, and I had to put that there, otherwise you wouldn't come, because everyone loves robots. There's reinforcement learning, which I think is, out of all the machine learning tools we use, is very, very applicable to the style of control that's required for robotics, and lots of other things too, by the way. And then I put deep in here, because deep neural networks are a really good function approximator for a whole bunch of stuff that we need, especially in reinforcement learning. This is not a talk on NLP, which a lot of people will be surprised with, because I've done a lot of NLP stuff. I'm sorry, we'll talk about NLP another day. What's funny is if this was a talk on NLP about deep reinforcement learning, 80% of it would be the same. And so this is an incredible part of neural networks, isn't it? It's all the same stuff. It's just rehashed. It's also not about shaving robots. Alex can talk about this later, but there's no shaving robots. Is this not working? Yeah, I can hear some reverb in my brain. Okay. Yeah, is that better?
Is that?
When you step to the camera,
yeah.
that much.
Yeah. I'll have to just be crazy.
Yeah.
Okay, so I'm going to talk about things in the context of some problems I've worked on, because that's how I frame everything in my head. And the first one I want to talk about is this very simple project. This is my first sort of when I was playing around with reinforcement learning project. I call it DriveBot. And everything we're going to talk about, we can just download later and you can play with it. This is a couple of years old, so maybe you've got to bring it up to speed or whatever. But this is the first sort of project I worked with where I was trying to play with some sort of RL in the context of a robot and maybe a car and stuff. So we're going to have this really simple problem where we're going to be driving this little bot around a track. And here's this little picture of the robot. It's very simple. This is this 2D world. It's very sort of idealistic. It's got this sonar. Everything's perfect. That's the software world. We'll come back to at the end of the talk about how we can transfer some of the things that we learn in these simple worlds into real world, which is where all that really matters. So I want to talk about the control of this robot and how it moves around the track using a couple of different terms. I'm going to bring them up one at a time. We're going to have this idea of an agent, which is the bit of software that we're writing for the control of things. And we're going to have some idea of everything else, which I'm going to call the world. And the world's sort of, how we get information about things. So that's sort of these two things we're going to talk about. The world, and again, just for terminology, again, the world is going to give us some state. That's sort of like our view of the world. And maybe it's a camera on a self-driving car, maybe it's an accelerometer, there's some sort of input. These are the things that we're going to make decisions about. And for this really simple first version of things, this state is going to be one of three values. It's going to be very simple, one of three values. Which of the sonars reports the furthest distance? Is it the one pointing to the front? Is it the one pointing to the left? Or the one pointing to the right? And that's what these green arrows represent. They represent some sort of idea of a simplistic sonar. So this robot is in the state of the furthest sonar being the front one. So this is like one of three states. The robot, when it gets this state, is going to make a decision about what to do according to some plan or some sort of objective. We'll talk about that later. And we're going to call that the action. Now this robot, again, the very simple robot, it's got one of three actions. We're going to start really simple. Go forward or turn left or right. So this is, the two views of the world we're going to care about. So we've got these three states, very simple, three actions, they're very simple. What we're going to aim towards doing is learning a function that maps between these states and actions. That's what these controllers are. I'm going to call that a policy. If we had this policy, you can imagine that given these states, we're going to decide some actions to drive us around the track. That's where we're going. So hopefully this is all pretty straightforward. We'll just build up. All machine learning needs a baseline. There's a very, very strong baseline for this problem, which you may have seen. If the sonar that is the furthest away is the forward one, you should go forward. If the sonar is the furthest to the left, you should turn left. And if the sonar is to the right, you should turn right. This baseline is very good and will get us a long way. It has some nuances to do with the gaps in the sonar, particularly here. So you might be pointing this way and getting a signal that thinks you can go forward, but then you clip the wall. It doesn't matter too much. I'm just going to say that this is a good baseline to work with. And the main point I want to make is we want baselines. Baselines are good for machine learning, this talk or otherwise. So now let's think about this in terms of a learning sort of thing. If we were thinking about supervised learning, hopefully everyone has an idea about this. We're trying to learn this function between states and actions. The way that we would do this in a supervised learning context is to get pairs of these things that we deem good according to some criteria and try to learn this function. So if you, say for example, recorded yourself driving around the track, you would collect these combinations of states and actions that you are in your brain deciding that represents this policy, and you could learn this direct function. This is called behavior cloning. It's very commonly done. And it's very successful, it's good, but I want to talk about this problem in a slightly different way. I want to frame it in what's called reinforcement learning. In reinforcement learning, we're going to introduce another concept into this. We're going to have actions like we had before. We're going to get states, but we're also going to get a reward from the world. The reward is not the same as the state, and it's not the same as the action. It's just going to be a number. And what we're going to do is to try to maximize this reward. So the world's going to give us the state of things, but it's also going to basically give us a pat on the head. You're doing well or you're doing poorly. It's not the actions and it's not the state. So our problem might be a little bit harder in terms of how the learning works, but our representation of what we want a good solution to be may be easier, because we're not talking about states and actions directly now. We're just talking about some function of the world that we maybe don't even see, which is good and bad. So for our problem, our simple problem again, the reward's going to be simple. If we said we were going to go forward, and we went forward, so we had some clear space, +1, you get a point. If you said you wanted to go forward and you didn't, maybe that means you hit the wall, you don't get a score. And any time you're turning, you don't get a score. So again, this is very simple. Hopefully this is a way of encouraging forward movement along the track. Now I haven't said anything about actions here in terms of training. Well, I guess I said in terms of go forward. But the main point I want to make here is these are not pairs of things directly. These are just sort of this scalar reward, which is neither an action or a state. So what's going to happen then, you can imagine, is we're going to have this, it's a sequential problem, isn't it? We're going to get a state, we're going to choose an action and get a reward and go to another state, of which we will choose an action and get a reward and go to another state. So there's this big sequence of state, action, reward, state, action, reward, state, action, reward, until some finishing criteria. We won't talk much about termination or whatever, but these sort of control problems are very much sequential. They're very much over time. They're not like the classification of an image where it's like, here's a picture of a dog or a picture of a cat. There's no sort of ordering in either of those. But these types of problems are very much sequential problems. So I'm going to decompose that sequence of state action, reward, state action into these little triples, or four tuples, I guess. So we're going to have a state that I was in, an action I took, the reward we got, and then the state we transitioned to. So these are going to be the unit we're going to talk about when we're learning. Where did we start? What did we do? What did we get a reward or not? And where did we end up? And it's really important to think about here the fact that this, even though it's a sequence, state, action, reward, this state is basically the first one and the next one, because we're going to make another action. These are the units that we will learn on from that sequence. So I'm going to go through an example really quickly. Again, I know this is a really simple example, but I just want to drill it in. Here's a collection of these events that might have happened in our simple world. We reported that the furthest sonar was to the left. We went forward and got no reward. So you remember that was because we hit a wall. And we're still the furthest to the left. So our view of the world, you can now sort of think, okay, it said left, I went forward, I hit the wall, and I'm still finding left, so it's not good. So I'm in the furthest left still. I turn left. You always get 0 when you turn, sorry, that's the rules. But now my furthest is forward. Okay, cool. I now go forward, furthest is forward again. I go forward and I get a +1, and my furthest is forward. One thing I want to make clear here is that what's interesting in terms of the sequential problem is that I got no reward here. But turning left didn't give me any reward. That was part of the rules. But it was important to do so that I could then achieve this +1. So one of the things that's interesting about these rewards as well is that they can be quite sparse. Even though I wasn't giving information here, because basically you're not getting any feedback yet, I got this feedback here. It wasn't because I went forward, because that didn't work before. And it worked when I was furthest forward, but I had to get there by turning left when it was left. So one of the interesting things about these sequential problems is that the reinforcement learning, again, even though it was simpler for me to describe the problem, because I'm just talking about the sparse reward, it's up to the learning algorithm to decide how to attribute this back in time. And that's going to be an important part of what we talk about. Okay, so algorithm number 1, how are we going to solve this? We talked about these representations, we talked about some sequences. I'm going to talk about I think one of the fundamental ways of learning this. I think it's pretty straightforward, and lots of other things span off this. This is the idea of Q learning. It's from like the 50s or 40s, so we're certainly not a new thing. This is an old idea, and the Q stands for the idea of quality. So again, we're going to learn a policy, state to action. That's our end goal, because that's all we really care about at the end of the day. In a state, what do I want to do? But I want to introduce a second, slightly different function that we're going to actually use to learn. It's called the Q function, Q for quality. In a state, if I took an action, what was my expected sum of rewards going forward? So, how well do I think this action will give me, not just immediately, but like into the future? And it's really important to talk about it as being a sum, because that's how we attribute this back in time, this idea of things later may occur. Even though it's going to be crappy now, maybe it's even -1 in the first step. Later, I'll get a +10 or something. So we're going to use this function to learn on, because it incorporates not just the state and the actions, but this reward, which is this weak supervision we're getting now, maybe quite sparsely over time. If we had that, that's good, because the inference now becomes this idea of saying, what is my policy on the state? Well, it's the maximum action. It's the best action I could take according to my Q function. So I'm in a state. I'm going to go through all my possible actions. Which one gave me the best Q? Because that's my best bet for the max reward over time. So this argmax will cause us some grief a little bit later, but this is where we're at. Especially, we're talking about discrete things at the moment, discrete states, discrete actions. It's okay for me to try this Q function 3 times and just pick the one that gave me the best Q. That's my best bet going forward. Okay, so how does this Q function, how do we learn it in relation to these learnable items I talked about, state, action, reward, state? Well, the Q function is this idea of expected sum of rewards. That's by definition, the sum of rewards going forward. What's good then is this Q function can be decomposed in terms of itself. Let's talk about this. The Q at state 1, given action 1, is going to be equal to the reward, because I know that, this is the reward I got, plus the best thing I can do from state 2. That's the nature of the Q function. It's the best thing possible. So I know at least from my state in action I'll get reward, because I just got it. This is what I got told by the environment. And then from then on, the best I can possibly do is whatever my Q function is for state 2. And so this nature of this Q function being defined in terms of itself allows me now to ground it in the reward that I know to be true. So what we're going to do is we're going to start this Q function, and we're going to use this style of update rule to slowly move the Q function towards this optimal. And we'll talk about that. Okay, so a very, very side note on a thing called value iteration. This is probably something you've seen about. If I have some value, so this is a bit abstract. It's very abstract. I'll represent abstract by literally waving my hands. So if I have some prior value in something and I observe a new value, one way to update my belief about this thing is just directly take, okay, I've observed a new value. I thought V was 5, now it's 6. Great, 6 it is. But if you don't trust your beliefs or you want to move things slowly, we can use this affine combo. It's a very common idea where we take whatever value we had before, maybe times 0.9, and then we say plus 1 minus 0.9 of this new value. It's basically, you can think of it as affine combo. I was at 5, I was at 6. You told me 6, I don't fully trust you, so I'm just going to move 1/10 of the way towards 6. And if you keep telling me 6, that's great, we'll get there eventually. But I'm just going to do things slowly. This is a classic, it's very analogous with a lot of the way that we use learning rates. I've got some belief and I want to get there, but I don't fully want to just jump in this huge big hit. I want to just slowly nudge myself towards something. So this idea of value iteration now can be used in the way that we do the Q function. So say Q gives us these random things at the start. And literally, in fact, if I just jump forward, when things are discrete, when these states and actions are discrete, the Q value can actually literally be a table, a 2D table. It's literally 3 by 3, yeah? We have 3 states, 3 actions. So it's a 2 by 2 array. I just randomly put stuff in, doesn't matter, just random crap. And when I get a reward, like an actual reward, I'm going to say whatever value is in there now, I know it's random, but I'm just going to nudge it a little bit. This is what this affine combo is, and nudge it a little bit from wherever it is now to a value which is a grounded reward plus whatever the best I can do in state 2. So your Q table, this is a Q table, it's actually literally a table, 2D table, will have garbage in it. But for every one of these that you know to be true, the world has told you, you're learning a little bit. You're using this reward to ground these values and just nudge them all into the right spot. Eventually, when the Q value is like perfect, you can imagine that these update rules don't do anything. Imagine that the Q value was, if the Q function, this table, was full of exactly the right things, then this values would already be equal to each other. This value here, the Q for state 1 and action 1, would actually be equal to the reward because this would be perfect. Does that make sense? This is sort of
Yeah. Do you keep like the time? If you're running an experiment, like engineering background here, if you had a robot, you want to start it off slow, so the activities that happen at the start of its movement might be different to a minute in or something like, or seconds in. Obviously, once something's learned a great deal about how to move, it could just go full bore at the start. Yeah. But is this essentially timeless? It doesn't care about where it is?
Yeah. Yeah, and so there's a couple of different ways I can answer that. I think I'll answer the...
That's right, you can just keep going.
Yeah, so you're talking about the idea that, if we have a large... So I'll rephrase this and tell me if I've rephrased it wrong. If I have a large number of these 4 tuples, some of them might be less informative than others because we sort of see the same ones again and again and again. Is that sort of what you're talking about?
In a sense, and I guess like you're just saying that basically every time you see the information, whilst you do have like the previous step, I guess you can kind of put many previous steps into play to modify this, but in this case you're just talking about a singular.
Oh, yes. Okay, so certainly this state, as we've described it now, is like this really simple 1 of 3 values. Just you wait, we're going to go through some crazy states, like crazy stuff. So yeah, I just wanted to really ground us in this idea of this thing, but yeah, we'll come back to some wild stuff later. Okay, so, but otherwise this sort of, generally makes sense. We've got this update rule, this Q value, and we're going to learn it from these grounded rewards that are telling us about this sequence over time. Okay, so I just want to talk a little bit again about this idea of the reward being sparse, because that was really important. We saw in that example I had of the 3 things, only the last one was a 1 and the others were 0. So if I think about a track like this and I think about my reward being, if you go forward, you get a point, and if you don't, if you turn, you don't, or whatever. That has some local optima which are painful. So here's an example. If you just go along for a while and then you do a 180 and then you go back and you do a 180, that's a reasonably good solution to this problem. So, optimizers are going to optimize. This is a classic thing, isn't it? they will find a good solution. And this is a reasonable solution for that problem given that track. It's actually it's pretty good to just go back and forth like this. So, you know, this is a classic thing. You know, we have to do a bit of hacking in a sense of like, well, hang on, that's not exactly what I know I told you to solve this, but actually I wanted you to solve something else. And so one of the good things about these rewards is it allows us to, you know, get around this pretty simply, because all we can do is say maybe let's just think about checkpoints. Let's think about these red lines that are checkpoints. And if you go over one of those checkpoints, I'll give you a point, and then you don't get another point until you go to the next checkpoint. Now, if we think back again to the supervised learning case of the states and actions, this rule we've now talked about is reasonably complicated to maybe express all the time. But what I just described here is trivial in terms of how we would rewrite the reward function. So being decoupled from the idea of what this state and action pairing is going to be from your rewards is super powerful, super powerful. You're putting a lot more onus on the learning algorithm now, potentially, to learn it, especially because you can imagine here there's a lot more zeros in that data. So there's a lot more sparse, which means a lot more data you need to gather. So these are the trade-offs we get, but it's, you know, certainly going to be the case we'll see where there are cases where we're going to express the reward and then we would have no chance of expressing the relationship between the state and the action. An extreme version of this might just be, say, you only get a point when you do a lap. That's pretty hardcore, and you can imagine that the amount of data you would need to collect in terms of, you know, banging into walls and whatever to eventually get this. The theory is sound, it would work, but the intensity of data you would require is huge. So these are the trade-offs we're talking with. There's also very fundamentally related to this is this idea called explore exploit, and we'll see, you know, this is a common thing in a lot of algorithms. I won't talk too much about it, but it's this idea that if we have these units that we're learning from, state, action, reward, state, there's some idea that, you know, over time we'll, you know, let the robot run and it'll do some stuff according to some, you know, policy maybe while we're learning, and so there's this fixed set of sort of state, action, rewards that we will collect over time. So if we're only exploiting the function we know, this is the exploit mode, we're only saying let's just do whatever we're doing according to the queue function, we're likely to not explore the space fully. We're likely to get stuck in many ways because we don't sort of have a chance to explore. And by exploring, I mean literally just doing random stuff. Like it's very common, you know, the simplest form of this is called epsilon greedy, where you just literally say, 1 out of 10 times I just do random stuff. The idea being that even though it's inefficient, you know, you're doing something random, you might hit the lottery and you might get us a little bit of info that shifts your queue function to now collect some more stuff. And this can be expressed in all sorts of interesting ways. Going back to this comment before about the idea of importance things, for example. If we were collecting a large number of these and we had some set that we had some confidence on, we weren't doing a lot of, when we did an update, we didn't get a lot from that update, we may choose not to look at those much as one that, like when we did an update on, it was made a huge change to the queue function. There's lots of ways of sampling from our data and then actually saying, even though, you know, I'm looking at this one more than I should, I can use a thing like importance sampling to say, well, I'll make my update a little bit smaller though. So there's lots of techniques we have to sort of explore these things that we're grabbing. Okay, discrete states and actions, that's where we started. So, you know, only 3 things for each of them. And this queue function is literally an array lookup, 9 values, very simple. So that's cool. The theory is all here though. We're going to back this theory now and we're going to start to talk about some more complicated representations. What about continuous states? Let's start with those. These states were coming from sonars I talked about, 3 float values. And then what we were doing was picking the one that was reporting the furthest distance. So here's another representation, a little bit, we're going to go back a little bit less sort of, you know, processed. And I'm going to say my states here are some form of a distance. So the sonar left, the sonar right, and the sonar forward. And maybe you can do the same with the actions too. Rather than just turn left and right, there might be some, you know, control on the motors. We can choose now whatever we like with these. But the main point I want to make is we're going to call these continuous. These are now no longer discrete sets. We have now some idea of continuous stuff. So we're going to talk about a queue function that's going to take now continuous values. What are we going to do? Well, this is not a talk on neural networks, isn't it? Of course, we're going to apply neural networks to this. So we're going to go back through all the queue stuff we just talked about, but in the context now of not discrete states, but these float values. So what's one initial way of thinking about this? Well, let's just make some network, it doesn't matter what it is, that takes the states. We won't talk about continuous states for now. Takes the states, so 3 float values, and then takes this action and just regresses to queue. That's a function we can use. Because it has some nuances, and you know, this is more going to be a bit of a talk on cool network hacking. We're not going to actually use this. We're going to use a slightly different one. And I'll talk about why. How did the update rule work? Well, we used the queue and the state and the action. That's what that network just gave us. We went directly to queue. But this second part of the update is that we actually need a max. So what would we do? If we had 3 actions, one way to get that max would be to run the network 3 times and then pick the one that was greatest and then use that going forward. That would work, but let's talk about some cool ways that we can optimize stuff. Instead of calculating a Q value for one action, let's get this network to calculate the Q values for all 3 actions. This seems, in some ways, you may think, oh, this is really wasteful, why are you doing all this work? But let's, again, think about how neural networks work. There's this lower levels of representations they learn, which are functions of the states. And then in this case, we're regressing to this idea of a queue. So this is really only 3 heads on top of a network. Even though we're doing this calculation of 3 Q values, it's certainly not 3 times the work of calculating 1 Q value, because the idea would be that these states would have some common internal representation, which helps us then calculate the Q values. Why would we want to do that? Well, let's have a look at how we can use it in some cool ways. First of all, we need to be able to calculate the Q value for a state in action. That's how the inference works and how this left-hand side of the equation works. It's really easy though. All we need to do is basically mask out the Q we care about, which value, with just like a one hot vector, 0, 0, 1, for example, if we were interested in the third one, and then sum the values up. So, I represent it this way. It's just like a dot product. It feels a bit weird, but these are, certainly differentiable operations, so they will work well in whatever we hook up later, and they are very fast to do, so it's not a big deal. So again, we're just going to mask out the one we care about, a 1, and the other one will be 0, and then just sum 0, 0 plus whatever the 1 value was would be the Q value. That's for the left-hand side. The max is really easy. It's just the max of the 3. So this is really nice. We've now got the ability to use this network in all the ways that the Q function is used here. For inference, it's just an argmax. We'll look at the 3 Qs. Which of the 3 Qs are actually the highest? We don't care about the value, so it's an argmax. We just care about which one was the highest. So now we've got this network, and we can use it in these 2 Qs. How do we do training? This is the killer slide, at least for DQN. This is an algorithm called DQN. This is the Atari learning paper you might have heard about, way back when, Min's paper. So what's this update rule? Again, it's the same update rule. State 1 in action of the Q is equal to the reward plus the max. So what are we going to do? This left-hand side represents state 1 in action 1. That's what we just talked about. I run the Q network, I mask out the one I care about, and I sum it. That's that Q value. This right-hand side is the same network, but with the max. So now we've got the Q of the left-hand side, the Q of the right-hand side. I'll add the reward, and I'll look at the difference. What I'm going to actually do is use this difference as a loss. I just run squared loss against this difference, called the temporal difference, because we're talking about the states over time. And I'll just use this literally as the loss for my optimizer. Why? Because we always want losses to go to 0. And if this loss was 0, what does it mean? If this was 0, it means that this left-hand side is exactly equal to the right-hand side. That's the perfect Q function. So we're going to use this idea of the temporal difference to train this network. And what's good about this is even though we had these actions here, which we maybe had like for the Atari, you've got like 9 positions of the joystick and then 9 for the button as well. You're calculating them all in one hit. You can run this for an update of this step in a batch mode in one go. There's one pass forward and one pass back. So I think this is a really elegant example of just some cool architecture hacking. This insight they had about this idea of the Q values, so that you could represent the whole side, and then the idea of the temporal difference is a really old idea. So that's a cool. This is the classic DQN. This is from 2015. This is what got people very excited about RL again for deep learning. Their states in their cases were the pixels on the screen, the actions were the controls of the joystick, and the reward was the delta between your last frame of the score. Now, there's a whole bunch of try to train this, and the main contribution of that paper were how you make this stable in training. And this is a talk for another day, but there's 2 really interesting things to do with an idea of a target network, and we'll actually address that a little bit, and then an idea of replay buffer, and it's to do with correlation examples. I don't want to talk too much about it now, but the main crux of this is that even though this is good, like all neural networks, you need to know these crappy little tricks to make it work. Okay, so continuous states, we're good. What about continuous actions? Why can't we immediately use continuous actions in this framework we've developed? Well, it's because we're calculating the Q value for all of them. We use a slightly different architecture and actually go back to what maybe we thought about as that first naive one. We're going to calculate 2 networks instead. This is an approach called DDPG, Deep Deterministic Policy Gradient, which comes out of DeepMind, and it was ICLR 16. This was a way of this is the first sort of example of using this algorithms for action spaces being continuous as well as states. We're going to train 2 networks, not just one. The critic is going to be sort of similar to what we talked about before. It takes states and actions and it gives us a Q value. So you can think it's exactly like a critic. I'm in a state and I did something dumb, 0. I'm in a state I did something really good, 100. So this is now responsible for telling us whether actions are good in a state. We also have an actor. An actor is directly what we talked about for the agent. This is the policy. What should I do in a state? So now we're going to separate these things a little bit. The reason for separating them, and we'll talk about how we train them in a minute, is that we're not now going to rely on this being discrete. This is now just a vector. And, in our case, it might be a vector of 2 or it might be whatever. We'll talk about more complicated actions as we go. How do we train it? Okay, so what we're going to do, we're going to train these in turn with each other. The way we train the critic is like what we did with the other one. We have an idea of a state from an action, and we want the temporal difference in the future to be the same. This is the Bellman update we were just talking about. But for the Q value for state 2, we're going to actually use the actor in this step. So what are we doing here? Actor, we want the actor to represent the perfect policy. Yeah? We're going to assume that, at least for now. So in state 2, what would the actor tell us to do? We'll use that to be our action for the critic to tell us in state 2 what the Q value is going to be. Everything else about this update is the same. So this is the same Bellman update we were talking about before, the Q value with state 1 and action 1, and how it relates to being grounded to the reward we actually got, plus the best thing that we could possibly get going forward. Because this actor is meant to be the best thing. As we understand now, this section of the document this network describes the Q value from state 2, because the actor will tell us the best thing it knows to do, and we will judge it. I put a little box around here to represent the fact that when we're training this, and I just wanted to introduce this a little bit, we actually normally don't pass gradients back to this step. So we're going to run a forward pass and a backwards pass, but we're only going to update this side. We're just going to basically drop the gradients for that. And that's to do with stability of the fact that we're actually making an update to the same thing in one sort of hit, which is a bit weird, this idea of a target network, and also very related to the replay buffers. I just wanted to bring it up here, but it's one of the big stability problems with training these networks, that you're telling it to do one thing while you're telling it to do something else. So we basically lock this out with a stop gradient, which is basically saying, use it going forward, but then for the reverse, just ignore it. I don't care, I'm just going to...
So that's a question about that. Are you loading anything into the actor about any kind of predisposition about what the problem is or anything like that? In this case, it's all loading.
Yeah. It'll, at the start, it's going to be doing crazy stuff, and it's going to be all over the place. And eventually, through these guys being trained in step, we'll just talk about how we train the actor in a minute. Yeah. They will in turn improve each other.
And my thought process in that was just like thinking about counter filters or other things like that.
Yeah.
Loading kind of like physical knowledge about how.
Yeah. This is all what we call model free. We're saying everything about the world and the relationship between these things has to be expressed in this network. This is a model free idea. There's no reason why, if you have a very good model that tells you things, that you can't incorporate it wherever you see fit in this. This is like the lower bound for if you didn't know nothing. Okay, so that's the critic. What about the actor? So what do we want the actor to do? We want the actor to be the best, sort of state it can be. Like, what is the best thing to do? We're going to now use the critic, and we're going to assume the critic is perfect. So given the actor, we're going to get a state. We're going to say, actor, give me the action that if you gave to the critic, gives me the maximum Q. So we're just going to do regression here. We're going to say literally, state to action, what was your Q value? How should I change my actor to make this Q value go up? Because if the critic was perfect, it would, basically tell you what to do. And in the same way like before, we don't apply gradients to the critic at this step. But neural networks, this is this amazing thing about neural networks. You just sort of bolt them together and you can work out, gradients with respect to bits and pieces as you see fit. So I can just, it's very easy to code this up. There's nothing inherent about either part that disallows this. But it's really easy to do. Actor, state to action. Okay, now if I gave that to the critic, what do they need to do? The critic tells me these gradients with respect to the Q. How should I make my parameters of the action change so that my action would have got a higher Q? So this is great. These two are training. However, we're now talking about training two things, and it's like even more unstable than it was before. But again, there's approaches to retain the stability. Okay, stability hell. It's all over the place. You're training this thing, you're training this thing, this thing's training these two things. We have target networks and replay. Blah, blah, blah. I don't want to talk about it. It's a pain. But they certainly. A lot of these papers introduce lots of tricks to make and heuristics to make these things faster. Heuristics everyone hates because it's like some hack, but we'll get there eventually. Yeah. Okay, so these were two very successful approaches, and we now have talked about this idea of continuous states and continuous actions, and this idea about how we learn this Q function to sort of learn this policy. Okay, at this point it was algorithm frenzy. People were going crazy. There's DQN, there's TRPO, there's double DQN, there's this continuous one, DDPG. Then how do you run, if you run them asynchronously, A3C, what about if you do this other thing, NAF, QProp, blah, 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 blah. It just goes on and on and on. So this is a very active area of research. Lots of people have lots of ideas that are primarily around stability and data efficiency. Because a lot of these techniques, to make stable, you need to run maybe, lots and lots and lots of data. And the most recent one was the distributed DPO, the Carpol paper from DeepMind. This is an awesome paper. A couple of these talk a bit more about a thing called policy optimization, policy, approaches. We've been talking so far about the idea of trying to calculate a value Q functions. So there's two sort of branches here that are related, but we've been talking mainly about Q functions. I think they're a little bit more easier to ground in our head.
Yeah, and special mention that ICML this year, that one of the DeepMind people was working on trying to sort of fit the entire distribution of Q values. Yeah. So it's like, not only give me the expected, give me the entire distribution of rewards.
Yeah. And that parkour paper is awesome. If you haven't seen it, it's the punching, the one where he's jumping over all the hoops and stuff. Yeah, it's awesome. Okay, so.
I want to see Terminator do that.
Yeah, exactly. And the Boston Dynamics. Yeah. Okay, so we now had some framework for Q values. We talked, it was a bit airy-fairy, but anyway, hopefully a little bit made sense and, it sort of grounds. We talked about some continuous states and continuous actions. And we also talked about a baseline at the start that was pretty good. So, I would find it hard to argue, let's make this actor critic DDPG network when the baseline probably did extremely well. But the good thing about this is it starts to allow us to do much more complicated things. So let's talk about some more complicated things. 3 sonars at 90 degrees, if then else statement. It's okay, fine. But this algorithm just naturally automatically works if you assign 5 random sonars. So here's a robot I made with 5 random sonars. Rather than 3 values, I'm going to have 5, and it just works. There's nothing to do. So if I train this, ran it over time, this robot would get better and better and better, and would learn to maybe ignore one of these because it's not related to the other. Maybe it would learn to ignore this. I don't know. But it starts to work. That's 5 random sonars instead of 3 sonars. Why not have random sonars per robot? No problem at all. Just stick some stuff more into the state. We can have now the state being the 5 sonar readings as well as the 5 angles that the sonars are at. So that we can now represent this robot being different to this robot, being different to this robot. Maybe per state even, not even per robot. So every time step now, because you can think in your head now what the neural network has to do. It has to now relate these angles to the sonar values to try to build one common representation, which is then used for the actions. So the good thing about this is that even though that if-then-else statement was clear for the 3, I'm not sure what my if-then-else statement would be for this. It's starting to get more and more complicated. So this is now starting to grow into more and more general states and actions because these neural networks are very, very, very good at building representations for that type of learning. Okay. Project number 2. So that was DriveBot. Let's talk about a different project. This is a classic control problem called the Carpol inverted pendulum. Lots of people would have seen this. It's a really simple problem. I'll go through it really quickly in case you haven't. You have a cart on the ground, which you can move left and right, and on top of it you have a pole with a weight on the end of it. The idea is that you start in this position, you get a random tap, and you have to move the cart to rebalance the pole. This is probably from like 400 BC or something. This is an old problem, yeah? So but it's fun in the dynamic sense that it's actually non-trivial to solve. If you're looking at this and think, that's an if-then-else statement again, it's actually not, and I encourage you to play with it because it's actually a pain, but it's a fun dynamics problem. And in this case, the two-dimensional version of this, we have what's common is a 4-state representation. The x, which is the position of the cart, x dot, which is like a velocity. We've got a first or a second order thing. Theta, which is an angle, and then an angular velocity, theta dot. So you want to know how fast it's falling, not just where it is. The action is just a force. Do we push left or do we push right? And again, the reward in this case is nice. It's just +1 until your angle gets past a certain point, and then you're dead. So it's a pretty easy state. There's 4 values. It's a pretty easy action, just plus minus 1 maybe, whatever it might be, and then a reward. So this is a classic thing. I wanted to make something a little bit harder. I made a thing called Carpol++. So this is a Carpol in a 3-dimensional simulator called Bullet that we used a lot at work. And the interesting thing about this is it's in 3D, that's one thing. But more interestingly, I made sure that the pole was not connected to the cart. So the dynamics of this problem is a little bit fiddlier. If you watch the start of this video, just about there, you can see the pole pivoting, not just from one center point, but actually rotating around. And then as it learns. So that blue line is just an arbitrary line, it's just a ray. But you can see that. So what's happening in this video is the cart at the start gets a bang, The controller is pushing the cart back to recover and then doing some small incremental adjustments. So, and you can see the main point I wanted to do here is that the pole's really light, it's featherweight. So when you make these cart movements, the pole's actually sort of, rotating around and doing all sorts of crazy stuff. So, talk about the state in a second, but the actions are just the fx and fy, so it's just the force. The reward's exactly the same as before, +1 until it gets past a certain angle from the z, and then it's game over. So let's build up some fun states. First of all, we're going to talk about the pole. And again, just let's think about what's the simplest way for us to describe the problem, not the algorithm. I'm going to use a pretty simple 7-dimensional sort of representation of this. There's 3 for the x, y, z, and in this case, it's a 4D quaternion. So I'm not going to talk about quaternions because they're crazy, but it's just a 4-dimensional representation of an angle or rotation. So this is just a convenient way. In fact, one of the main reasons to get this is from the simulator, from Bullet. When I say, give me the position and orientation, this is what it gives me. So that's great. I literally will grab it. It's a convenient, I want to make sure I express it. It's a convenient way for me to express it, not the network. Maybe orientation's a terrible thing. But anyway, so we've got the pole, that's our start. That's seven values. We've also got the cart, because it's connected to the cart, remember? So I need to know I'm going to use the exact same values for the cart as well, x, y, z, and the orientation in 3D space. And so I've got a 2x7 now. I've got a matrix, a 2D matrix, that I can flatten to 14 if I want. But it's 2x7. The first row is the cart, or the pole, or whatever, and the second row is the cart. So it's 2x7 now. We need to know velocity, because this problem's not just about time step, it's about how far it's falling. So rather than talk about things in terms of velocity, I'm just going to give you 2 pairs of positions. And if you need velocity and you think it's interesting to solve the problem, then that's great, you'll solve the problem using it. So now we're talking about 28 values, 2 by 2 by 7. The first axis is time, so over 2 time steps. The second axis is the cart versus the pole. And the third axis is the pose, of which the first 3 are Cartesian and the last 4 are orientation. Again, I'm just, whatever I think is useful for me to give you that I think you need, and you just work it out. So we're talking about 28 values now. And again, let's go even crazier. Why not images? Forget about poses. Let's talk about these networks being good for control. And in fact, that last picture we saw was something that wasn't being controlled from that 28-dimensional vector. It's being controlled from an image that looks like this. So this is it's actually, forget about this debugging info. This is just the only GIF I had because my computer's literally was just come off a boat from the other country. So this is the only thing I have on my laptop. But so we have this idea of an image, literally just rendered from the thing. Forget the pose. You now need to, as a computer, solve this in terms of an image. That's fantastic. Convolutional neural networks, I'll just bolt literally on the bottom of what we've talked about so far. So an image is, in this case, it's 50 by 50 by 3. That's just what we have. So height by width by channels. In this case, things are clearly red and green, which is nice for the learning at least. And like we talked about before, we need it over 2 time steps though, at least. So this data is actually 2 by 50 by 50 by 3. And just for the convenience of how we use convnets, I'm just going to basically concatenate that 2 timestamps into 6 channels. So you can imagine now that instead of having 3 channels, red, green, and blue, this thing's going to get 6 channels, red, green, and blue at time step 1, red, green, and blue at time step 2. So it's 50 by 50 by 6 instead of 50 by 50 by 3. For convenience for me, because it means that I can just use off-the-shelf 2D convnets. It also reflects the fact in this case that I think about there's some interesting correlation between a single pixel over 2 time steps, because what I'm doing is I'm actually putting them in the same spatial coordinate. And I think that's reasonable and sort of does make sense. And to be honest, even if it didn't, it would learn and do the right thing. So just because I wanted to talk about it here, this is the fun thing to do with once you start to, represent something, you can start to do whatever you think is interesting. So maybe instead of channel concatenating immediately and making it 6, I might choose to run this through one conv layer and, build up maybe 25 by 25 by 8. So I'll do one sort of pass over this in terms of a conf pass. And then do the same for the second image, and then channel concatenate and tie these weights. And maybe there's some argument that my initial processing of the first frame should be exactly the same as my initial processing of the second frame. It's okay to share those weights. This is the sort of thing that you maybe want to do later if you're thinking about how do you start to save parameters. because this has less parameters than the previous one. It doesn't matter too much, don't need to think too much about that, but either will work, and especially in this very simple problem. Okay, there is a small problem case though, and what's interesting about these things, and it actually comes from this exact example we've got here. So this control was pretty good, but if you see how it runs now, you'll see when it starts, it manages to balance it, and there we go, unbalanced, and then it's like, whoa, what happened? It fell over. What was it doing wrong? What's interesting about this is that the way I was rendering this image is, you might not have noticed, but I had the zoom in enough that I was cropping the top of the pole. You never see the top of the pole here. I hadn't even noticed myself. What it's doing is that I was noticing that one out of about 20 would drastically fail during testing. And the reason for it is it's balancing the pole, but then the pole is falling in line with the camera. And the resolution is such that you don't notice it. So if you look at it, try to see it, you just can't see it. So it balances it, and then it's falling. I can't remember which way it's falling. It's falling forward or back. Falls past the position where its velocity is now, it can't retain it, and it does this crazy move to try to recover. Well, what's the simplest thing we can do? What about we just point two cameras at right angles? So instead of now having one camera, let's just stick another one in and render it twice. So now we've got two cameras by 2 time steps by 50 by 50 by 3. And again, what's the simplest way to put this into a ComNet? Just concatenate those channels. So now we've got red, green, blue, one camera, one time step, red, green, blue, second camera, second time step, blah, 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 blah. And we get 12 channels instead. And again, this just works. It's great. And in fact, when you've got batching, because you want to always batch things, we end up with 64 by 2 by 2 by 50 by 50 by 3. And if you're like me and you judge yourself by the size of your input tensor, it's like, yes, 60 tensor, that's pretty good. Before the concatenation at least. So you can also, rather than having two cameras, this is an experiment I did where one would have one camera and allow it to move around. So now our state's going to be 2 time steps by 50 by 50 by 3, plus the current angle of the camera. And the action is going to be the cart movement plus a rotation of the camera. And what this learns to do basically is learn to keep the camera at right angles to the pole. So as the pole falls down, it will move the camera around to give it more information about the fall, and it will balance. So this is again a great example of the reward is not changing here. All I'm doing is changing the states and actions, and the controller is able to pick these things up. These are pretty, complicated. They're starting to get more and more complicated in terms of the control. Okay, everything we've done so far, no robots. Let's look at some robots. And for the robot part, it's going to be interesting because we're going to just basically rehash all the things that we've just now talked about. Continuous states, continuous actions, and how we would apply them to some specific robot problems. So this is the KUKA Iowa. It's a fantastic industrial robot. It's about yay big. It's quite expensive. I think they're like 100K or something. But the accuracy and precision of these robots is astounding. Like they are able to move in these incredible ways. And one of the reasons why they're really, really expensive is because the sensing and actuation of these robots is spot on. It's awesome. And so a lot of the times, I think about these robots as being incredibly expensive because of the hardware. But the software control of these things is, it's not too complicated. So we've got a lot of motivation to try to say, if we had cheaper motors and cheaper sensing, could we move a lot of the control problems into software? Because if I want to make one of these robots to put in everyone's house, I need the robot hardware to be cheap, even though the complicated software maybe comes along for free, basically. You just copy the software, yeah. So the setup I'm going to talk about is the one that we've been primarily using, that we used at Google, which is this idea of grasping. Grasping is like the classic first problem you need to solve if you're going to be doing manipulation. If you want to screw something up? Oh, sorry. Yeah, so if you're going to be doing something and you want to be doing manipulation, what's the first thing a robot needs to do? It needs to pick something up. So this is the classic setup we use for grasping. And so the idea is we have a bin with objects in it, and this robot's sort of going in and out of the bin, picking stuff up. Now in this case, we've got lots of options of how we represent state and actions, and then rewards. So let's go through them really quickly. Oh, before that though, one really important thing, and this is one of the main things I was working on, is this idea of the robots are great, they're fantastic, there they go, doing this awesome stuff. If we've got 6 robots here in one of the labs, and they're $100,000 each, and they're running in real time, and you can see how long it's taking to collect. This is at 4 times the speed because of the safety thing. It's going to be pretty expensive to gather a lot of data. And so this is great because this is the real world, and that's actually what we care about. But what is super important is how do we solve these problems in a simulator and transfer it to the real world, because that's the only way we're going to make these things scale. So this is an environment that it's a little bit different to what we use, but it's exactly, you can download this right now. It's by this guy Erwin, who wrote all our tools, and Erwin's awesome in terms of this physics simulator. He has an Oscar for doing this work because of His toolkit is in like every PlayStation and every movie you've seen probably. And he's built this thing which is basically a simulated version of what we just talked about. We've got a tray, we've got the robot, we've got a gripper, and we've got some objects we're going to play with. So I highly encourage you to have a look at this framework. It's pretty awesome. So let's think about what our states were going to be. So everything we talked about before is very equivalent in terms of it being continuous. We might have this robot is a 7-DOF robot, so it has 7 degrees of freedom in the arm, and it also has this end effector in this case is a gripper. So the state of our robot can be as simple as the positions or the velocities or the torques of the arm, and then whatever we want to do with the end effector, maybe open and close or whatever it be. And it's also very interesting for us to think about the state in terms of images. So if you see in that middle image, we've got some cameras sitting up here that are looking into the tray. And so we've done a lot of this work includes, we've got to make sure that this robot is able to do things based on an image. Because even though we might have a lot of information about the arm, we don't have ground truth information about things in the tray, for example. And so being able to relate the arm and the objects in the tray is good, not just for the fact that we're picking up the objects, but also because potentially the robot can start to infer information about its arm from picture rather than from super expensive sensors. And so all the learning we just talked about is exactly the same though, because we talked about how we stick some arbitrary numbers in and we talked about how we would stick some arbitrary images in. So that's our states. The actions are sort of equivalent. We've got some joint controls for the robot and we've got sort of control for the gripper. There's different levels as well of how we want to talk about things. We might want to talk about things in terms of the raw angles of joints, or we might only actually care about the position of the gripper. And so there's a lot of things that are available to us in terms of like inverse kinematics to say, actually, I just want the gripper to be in a certain point and you work out where the joint angles will be. But the point of this is that the neural network can decide to work in, you might want to work in velocities, or you might want to work in torques, or you might want to work in this pose of the end effector. The learning algorithm is the same. What suits your problem, it's fine, it'll just work. Well, it doesn't always just work, but it should just work. Rewards, again, this is interesting because we have these 3 things, didn't we? States and actions and rewards. For the simulator, it's great. Everything actually that we're sort of talking about so far, it was simulated in a way, wasn't it? We'll come back a little bit. In terms of that first one, we'll talk a little bit how it transferred to the robot, but to a real driving machine. But for now, let's talk about it in the context of this robot. So we have ground truth in the simulator, that's great. Ground truth not just for the arm, but also for the objects. But it's a pain in the real world. There's like endless. We might have lots of information about the robot arm, but we don't have much information about the objects in the tray. And so one of the good things about weak supervision as well, this idea of using rewards, is it doesn't have to necessarily be perfect. So there's all sorts of simple heuristics you can stick in here. So one of the things that we did for grasping, for example, is we would take a picture of the tray with the arm away from things and look at it. We would then go and do some stuff in the tray and then pull the arm up. If the arm thought it had something in its gripper and the image now looks different, success. So this is a very high level, there's a lot of cases where that will get wrong. But the whole point of this as well is it's easy for us to describe the problem in this weakly supervised way. I'm just literally saying image difference, 0 or 1. I'm not talking about positions of objects or like the arm or anything. It's a very, very abstract reward from states and actions. But yeah, the real world is a pain. It's slow, things break, they fall over. What a pain. Another thing that's super important, and this is a little bit just of one of those things, that, and I hate this actually, this idea of reward shaping, but anyway, so one of the things that we might talk about is if we're interested in training to pick something up. So how do we represent that picking up? Maybe we're going to say how high off the table it is. That's going to be my reward. But you can imagine here that if you had a learning system that's trying to learn this, at the start the robot's doing all sorts of crazy stuff, and it has to be by accident it somehow manages to move or to pick something up. And that seems like a very unlikely event. So what's really common, you see a lot, is this idea of what they call shaped rewarding. And in this case, the shape reward might be the distance off the table of the object we're trying to pick up, plus some smaller magnitude value times the distance from the gripper to the object. So even though we don't care about the necessarily being close, we use that second term to sort of encourage you to move near, and then when you start to accidentally pick up, the first term takes over. I really, there's something that irks me about this sort of idea of like this, where this combo. Yeah.
Why not using the inverse reinforcement learning problem?
Absolutely,
Yeah. Instead of feature extraction, different kind of rewards function for that.
Yes, inverse RL is certainly. No, it's certainly very, very applicable to these types of problems. But a lot of the time people do this, and this is a bit of a general statement about shaping, but yeah, inverse RL is certainly another way and probably more accurate for the grasping problem. But yeah, too many RL things to talk about. Yeah, but that's a good point.
It's full employment. You want to make sure that there's always something to engineer. They can engineer reward functions.
Yeah, I just hate it. Yeah, it's exactly right. It used to be like you'd always engineer features, and then it was architectures, and now it's reward functions, and it's just like, yeah, we're always in a job, yeah.
Learning policy itself also. The kind of learning to learn and learning by learning.
Yeah. It just we'll always find something to do. Yeah. Okay, so I think I'm getting close to time, so let's go through this last bit quick. Let's talk a little bit about some transfer stuff. Actually, this is the main thing I worked on, the idea of transferring between the simulator and the real world. Because, it's easy for us to gather hundreds of millions of examples in the simulator, but if they're completely different to the real world, then they are useless when we try to learn a policy that's for the real world. So we need to be able to relate these two things together. So I built this little robot. This is the equivalent, the equivalent of that simulated one. So it's got the same sort of thing, wheels, and it's got sonars. Unsurprisingly, the sonars behave extremely differently to the simulated ones, but that's okay. That's the point of these sort of experiments, to talk about how far you can have them being different. So I'm going to talk about two approaches to things. They're both in the adversarial learning context, and I think the adversarial learning is actually probably the most interesting idea in neural network training, I think, in the last 5 years. I think it's a really fascinating idea, and I'm going to talk about two sort of slices and versions of it. The first one is pretty awesome. This is the first one I played with. It's called domain adversarial learning. So I'm going to, again, let's be a bit abstract here. So I have some idea of some states, and I'm trying to learn a mapping to some actions. And what do neural networks do? They learn these intermediate representations of things. This is very vague again. This is squares and triangles and stuff. But this is a common idea in these networks. Take some input and then some changes to them, often with non-linearities, otherwise what's the point? To regress or to set of actions in this case. What I'm going to do in this case is I'm actually going to stick another little network onto the side. So I've got two networks here that are sharing some parts of themselves. The one on the left-hand side is the main one that's mapping from states to actions. And what I'm going to do is I'm going to feed this network examples that are states from the simulator, and I'm going to also feed it examples that are states from the real world. They're both going to go up from the bottom. So that S bit is either real or simulated. And what I'm going to do is I'm going to use a second network off to the side, and its job is try to classify that state and to say whether it's real or fake. So it's nothing to do with the actions. This one off to the side, its only job is to try to work out if that state is real or fake. So let's think if we were training these two things together. The left-hand side, from states to actions, what is it trying to do? It's trying to make these representations here useful for the goal of mapping from states to actions. That's what this left-hand side does. What is the right-hand side doing? It's trying to say, what are the useful features that I can use to distinguish whether the state is real or simulated. So in many ways, these two networks are in competition at this point. They're adversarial to each other. This network wants to change these features for its purpose, S to A. This network here wants to change these features so that it can tell the difference between states that are real or simulated. So this is an easy label for us to get because we know whether they're simulated or real. So it's really easy to have these examples, and we've got these examples already. Now the trick is, it's a really cool idea. It's really small font, so I'll read it out. It's to reverse the gradients. So what does this do? In terms of how back we go forward, and then we have some idea of gradients that tell us how should you change yourself so that I do better at my job. This network's job was to tell the difference between real and simulated. If we take the gradients it's telling us here and do the opposite, we actually change it, this network says, hey, it's harder for me now to tell the difference. I wanted it to be easier, you're making it harder for me. What are we doing when we're making this network's job harder? We're removing any information it knew from this part of the representation that helped it tell whether it was real or simulated. That removes the same parts of the representation for this network to be able to now operate on things that were explicit to the real or simulated. Because networks are incredibly exploitive. They will find whatever they need to find to do their job, regardless of whether it was something that was only in the real or simulated. They don't care. So by doing this, we need to give this network more capacity. But what we've done is a form of domain regularization. We've now said that these representations here are now squeezed out in terms of whether they were simulated or real. These guys are adversarial to each other, and it's called domain adversarial, because we're now saying that this guy can't do its job, and this is domain regularized. I think it's a really cool idea. Again, because networks are playing against each other, there are pain points, but it's a really, again, cool idea about the fact that these networks are extremely decomposable. 3 networks are at play here. We're actually going to do this trick where we reverse gradients. This is a very simple, it's a very simple idea at its core, but it's very, very powerful. So that's one thing, and that just works for this problem we talked about with the simulated robot. It learns to standardize across these things for whether they're real or simulated in terms of if you just union the set. So it was an easy thing to do anyway, but it was a proof of concept, and it certainly has worked for other examples of robotic control with simulated and real images that are in papers that have not been released yet. Maybe if I do this talk in a month, we can talk about different stuff. Anyway, so the other one that I think is interesting is to do with the same idea of adversarial learning, but in a generative context. So this is a really cool architecture. It's called Pix-to-Pix. You may have seen this. It's a really cool idea. And I don't know what everyone has done in terms of GANs, but I'll just give a very high level of view of things. What we're going to do is we're going to try to learn, and I wasn't allowed to show the robot pictures, but this is the same sort of thing, but with, say, simulated maps and real maps. This is a translation between a satellite image and a map that looks like Google Maps. What we're going to try to do is we're going to, rather than make a network which is able to be fed simulated or real images, we're going to make another network that translates between simulated to real images and then use those real images. So we'll train everything based on the network thinking it's got real images, but we'll just use this other network first to translate simulated one to real one. So I'm going to call this the simulated one, and it's going to try to translate to this real one. So all we really care about at the end of the day is this network, the G, the generator. Simulated to real, that's our end goal. How do we train this thing? What we're going to do, and this is the classic Pix-to-Pix model, you might have seen the example of one where you draw the one with you draw the line drawing and it makes this ridiculous version of like a weird cat or something. Human. I don't know if you've seen this. It's really disturbing. It's awesome. This is the same paper, same model. So what we're going to do is we want this thing that translates from one domain to another. How do we train this thing? So you probably talked about GANs before, but I'll just give a quick summary. What we're going to do is we're going to have another network called the discriminator, and it's going to take pairs of images, not just one image, but a pair of. It's going to take either real pairs, so these are from a ground truth set, and what it tries to do is, well, D's general task is to try to say, is this a real pair of images? Is this really the real version of this fake image in terms of this pair of images? So sometimes we feed it real images, that's like one form of it, but another time we also feed it this one, but the image that came out of G. So again, this D is a discriminator. It's trying to tell which are the fake ones and which are the real ones, which have come from G. And again, so there's this adversarial play between the two. At the start, if G is doing crazy stuff and just generating like, bright red images, at the start, if this is mapping to bright red images and you showed it a bright red image versus this, D's like, oh, that's clearly a fake, you're terrible. But we use the gradients from that decision to make this decision a little bit harder, and G gets a little bit better. So we've got this idea of a counterfeiter and another one that's trying to tell. And so at the end of the day, these play against each other. The D gets better and better at telling the difference. The G gets better and better at making fakes. So at the end of the day, all we really cared about is this G, and that's all we use at the end. And so it's able to simulate, it's able to translate between the simulated versions of images and the real images. And in fact, if I go back to here, I can't show you exact pictures, but I can show you one thing. If you look at one thing it does, which is really cool, I don't have a view of the simulator here, but you can see in this simulated image, the arm is very simple. It's flat shaded, it looks pretty fake. The real one has a logo on the side here, KUKA, that's the logo. It has things like these cables and stuff. These would all be things that if I took the rendering out of that, because you can just do a rendering, do you or do you not have cables? That tells you whether you're a fake. Do you or do you not have KUKA on the side? That tells if you're a fake. This G actually learns to draw these things in. It learns to put cables in that are realistic. It learns to write KUKA on the side. It learns to cast a shadow from the arm down into the tray, because these are the things that D could use to tell the difference. So it's really powerful because now we've actually ended up with this as a network that can basically translate the rendering that comes out of this very simple simulator and make it look realistic. And the rendering from the simulator can be very simple. It can even be a segmentation mask, like literally like a big green blob for the arm, a big red blob for the tray, and it'll learn to draw textures and whatever it needs to do to fool that discriminator. So it's super powerful because now it's a way of taking the simulated data, of which we have huge amounts, and turning it into the equivalent domain of the real data. And that's it. Thank you so much. I don't know, was that on time? I don't know.
Yeah, that's pretty on time.
Yeah.
We'll do like...
I have a tick in my head.
You did well. Yeah. So we'll do maybe like 5 minutes of questions for Matt. Like, yeah, maybe we'll do 2 or 3. Anybody from the audience?
Yeah. Jump in, but I'll ask if anybody else wants to.
Yeah.
I'm curious, I read an article talking about how the kind of wanted position for teaching, say, robots to do a task is rather than kind of holding its hand or manipulator and grasping and placing a mug on the shelf, it's home help, whatever, is you kind of get the mug and you say, watch me, and then you put it on the shelf and try it a few times. And it's a bit like I Am Groot in the second iteration where he's trying to deactivate the bomb or whatever. If people have seen Guardians of the Galaxy 2. He gets it wrong every time. But it's basically, I'm curious as kind of the role in which adversarial approaches like you just talked about might play in that, and how quickly they can use, say, some basic instruction, run that then through a whole lot of iterations, using that as an input, and then actually then play that out in their own adversarial approach, just like showing a bad image, and going from that. Has any research been done to provide some base level interaction and then run that heavily through adversarial and bring in like past experience of how the manipulator moves and other things like that, and how grasping works and all the rest of it, like all those things together?
Yeah, I can't think of any directly relating to that. Oh,
could you just repeat
so the idea
that?
is like, you know, what everything I just talked about is model free so far. It's actually to learn from its own examples completely randomly. And what you're talking about is the idea of imitation learning, where we have, you know, humans are able to do this already, so why not use them to seed sets?
You might have like a model where a robot knows how to grab a mug, it just doesn't know where to put the mug and how to put it up there. And you actually then say, okay, it's not a mug now, it's a teacup. This is how you hold a teacup, and this is how we have to go on the saucer, for instance. But
so it's worth checking out. At ICML, I think Sergey Levine and also his PhD student Chelsea Finn are working on kind of adversarial models, but for demonstration learning, like learning from human demonstrations. So it's definitely worth checking that out.
Okay, because it strikes me as one of these things where you just have to know what the teacup's delicate, so there's a certain way you move it, all these other things, but you can basically borrow from the whole mug library.
Incorporating physics is definitely important as well.
And I think a lot of people think about these things from, like, especially from the model free thing, because it's like a lower bound. It's like, this is the best we can do. But everything you just talked about are very, very practical things to actually solve this much quicker than it would be if you just completely experimented. But yeah, I think a lot of these things are very composable. So if you have some rough idea about how they can be mixed and matched, the toolbox is available.
Maybe, one more at the back.
Hi, I'm curious about the reward. So that currently most of the research is in reinforcement learning. They have engineered the reward signal. So is there any like important research on learning the reward automatically, like without having to engineer the function to generate the signal of the reward or something like this?
I guess, you know, there's a whole class of this, which this other chat brought up to do with inverse reinforcement learning and trying to learn these things. So it's not something I've done a lot with, so I wouldn't be able to send you like a link to any canonical papers, but there has been a lot of work with it. So
can I add to this? A couple of tool mechanisms for those algorithms called maximum entropy. It has a deep maximum entropy kind of thing, kind of a cool application using that in autonomous driving. And this one to how to learn the reward function. And also there's a Bayesian kind of version of that also learning the reward function. You can check the maximum entropy in versus reinforcement.
Thank you.
Yeah, another thing that's worth checking out is there's a guy at ANU named Marcus Hutter.
Yeah.
Yeah. Who,
In ANU, yeah.
At ANU,
Yeah.
and that he does, part of his work has been on like knowledge-seeking agents, so to come up with reward functions which represent how much have you learned, and then try and maximize how much you've learned as opposed to one specific objective. So
Yeah,
that's
cool.
worth checking out as well.
Yeah.
There's a PhD student he has named John something. I'm sorry, John, I can't remember your name. But
Yeah.
he was a huge guy.
Sure, so thank you.
Maybe. Thank you.
Yes, from your speech, I have got the action, reward, and the state of a robot, and also I understand the generator and the discriminator of the adversarial network, but I still couldn't get them together because you said that it will determine whether it is the real or the simulation. So the real is what a human would behavior, right? So the simulation is the robot would generate. But this should be done before the robot.
Yeah, I was more meaning in terms of the. Okay, so you're asking about the difference between the real and the simulated?
Yes,
Yeah.
I can't get exactly what is the simulation state for the robot.
Yeah, so in this case, in terms of the what's the difference between the real and the simulated for this adversarial stuff? I was less talking about the idea of a human versus a robot, but more if you think about the RGB rendering from a real camera, so a snapshot from a real camera, versus what might be coming from this simulator, it might be a lot simpler in terms of its lighting, in terms of its textures, in terms of the model itself. So this thing in terms of the GAN, which is trying to do the translation, is trying to translate between this maybe very pixely image of things that is like flat textured, it's from the simulator, maybe it doesn't have parts of the model, it doesn't have textures, and it needs to translate it into an image that came from a real robot, from a real camera. So it's all the things that are basically changing the perceptual side of things, not the dynamics of the system, in terms of like what color is the arm, what color is because if you think about, if I train the simulator, say for example I train the simulator, this whole system we talked about on the simulated data, and the simulator looked very unrealistic, like it had no texturing, it didn't have lighting, for example, no labeling. If I tried to just directly use that model on a real robot, the differences in the images it's getting are so fundamental that it wouldn't be able to learn. It's basically like you'd start to see textures and the cabling and the writing of KUKA. It's totally, the distribution of the images in the real world would be totally different to the distribution of images from the simulator because they look so different. So the idea of that GAN is to say, can we translate between the two? If in the simulator I put the arm and make it look like this, and I have a picture of the real arm that looks like that, that can be paired data that I can try to, basically it's a form of translation. Can I translate between an simulated image to a real image? It only covers the perception side. So this generator needs to do things to make that image look real, like drawing on cables or drawing on KUKA. It's not necessarily talking about the dynamics of the system, but it's about translating the image. Does that make sense? Yep.
Awesome. Well, that was a great presentation, and let's all thank Matt.
Thank you.